Hi, my name is Lillian Wilson-Wade, and today I'll be discussing Lab 5. In Lab 5, we were given the opportunity to apply what we've learned from this course to understanding the physics behind an interesting situation. I decided to look at the extreme rope swing. Today I'll be creating a computational model of the interaction as well as examining the effect drag has on the system, and I'll also see if it fulfills the energy principle. The key concepts to understanding this lab are the energy principle and Newton's second law, as well as Hooke's law. Hooke's law is going to help us because we'll be treating the bungee cords as a spring, so we can find that force is equal to the negative spring constant times the stretch. Using Newton's second law, we'll also be able to update the object's velocity and thus position as it moves. And through the energy principle, we know that the final amount of energy should be equal to the initial amount of energy in the system. The change in energy should equal 0 because energy should be conserved throughout some interactions. To set the initial conditions for my model, I looked at the behind-the-scenes video the jumpers also posted. In the video, they said that the rope's length was approximately 45.72 meters long, that the length of their fall was approximately 39.634 meters long, their distance from the ground was approximately 3.048 meters long, and the time that they swung in the air was also about 20 seconds. For other conditions, I researched the average mass of a human as well as the average spring constant for the type of rope the climbers used. After finding these models, I created a computational model of the object's motion. I first changed the initial conditions to match that of the situation and computed the energies of the system using the equations to determine kinetic, gravitational potential, and spring potential energy. I edited the wall loop to calculate net force using gravitational and spring forces, and also to update the ball's velocity and position using Newton's second law. I also updated the spring's length and stretch in this loop and found the energy changes by finding the new kinetic, gravitational potential, and spring potential energies at the new position and then just subtracting the initial ones from them. When the program is run, it looks like this. The red represents the change in gravitational potential energy, the blue represents the change in kinetic energy, and the green represents the change in spring potential energy. The yellow curve is the total energy, and it's at 0, which shows that the energy is conserved throughout this interaction following the energy principle. Now let's look at the effect that air resistance or drag has on this model. The drag force acts opposite to relative motion and is proportional to the velocity squared by some constant, which is represented by b. To calculate the net force, we add the gravitational, spring, and drag forces together in the computational model, and when we run the code, we see that the drag force affects the motion, keeping the jumper from completing a full final arc, and also results in energy being lost from the system. This makes sense. The air resistance would cause the jumper's arcs to slow down and become smaller in width in real life. Finally, we can say that yes, the energy principle is satisfied as the change in energy remains at 0 throughout the interaction modeled by my code.